How's everyone doing? Okay, all right. Okay, good. You guys ready for a pop quiz? No, fuck no. But you see the little heart attack you had? That's why we don't do exams. They're anxiety provoking. And they only test your knowledge at one instance, right? What do you want to know? Whether or not you did well the whole semester. So I'm going to use all of the data points throughout the course of the semester. I want your knowledge to do this. I don't want your knowledge to do that, right? Okay. What's this? Yeah. Planets to scale with each other. Good. All right. What's this one? Someone new. What's that? I don't know where that's coming from. Okay. Mercury here. Good. Does Mercury really have this little line out of it? No, this is a color mosaic. It's multiple pictures added together, and they're missing data right there. Okay, that's fine. Okay, what's this one? Venus. Everyone got that one. Okay. This one? Thank God. That one's Mars. This one? Mars, right? And Mars is cool. So this picture of Mars is particularly interesting because this is to scale. So this is largest canyon system in the solar system. And if you just imagine how big that is and place it on Africa, like the width of Africa. So our largest canyon is, of course, the Grand Canyon. And that is like several states. That's pretty cool. But it's not like the width of the US, which is about how big this is. What's that? Pluto. Okay, interesting. Is it the moon? Moon's pretty big. It's actually bigger than that. Yeah. Yeah, is that what a Mars is? Ah, interesting. Okay, now Mars has two moons. This is a planet, a dwarf planet called Ceres, that lives in the asteroid belt and is round. So we'll talk about that, not when we talk about the moons and the planets that we're talking about now, but when we talk about what we call small bodies. So it's the largest of the small body. Pretty big. Okay, so today I told you that we're going to be doing check-ins this week. And we're going to have a document that will be posted today that will describe my expectations. So you've had lots of warning about this, right? Okay, you're excited to try this? Medium, maybe? Okay, that's a lot of pursed lips. So I'll talk about these expectations. They'll be submitted next Tuesday. So you'll have the opportunity, of course, to do the homework, and then over the weekend you can reflect on everything you've done so far. They should include full sentences. I'll say this over and over. If your homework currently does not include full sentences, work on that. I'm going to ask you to reflect on your performance so far. So when you talk about homework one, don't say, I got all of homework one done. It's like, I got all of homework one done. I felt I understood it, right? How did you feel about that process? I didn't understand this component, but when I went and I read the book, it made more sense to me, right? Did you learn at each of these steps? Okay. And then you're going to describe whether you're meeting, exceeding, or failing your personal expectations for the class, right? What goes into it? So I want a physical packet that I can hold. I'm going to hold and mark it. So I'm going to include your homeworks and any revisions, whether they're graded or ungraded. So let's say you got the homework back and you made some changes, but you're like, well, these are really just like small. I don't need to turn them in. That's perfectly fine. Just include them so I can see that you made the changes, right? Please use a paperclip or a folder or something. If it's just loose paper, it will get like lost. So just try to keep them together. You can use a stapler. I don't mind, but that's harder for me to hand you back individual pieces, right? Okay. I need your clicker ID number. So you have a clicker, you've been using it. On the back, it has the clicker ID. This is how I'm going to pair who you are to the roster that is developed by iClicker. So I need that information. And then after that, I'm going to post the roster so you can see how well you've been doing in the class, just attendance wise. Have you been participating? Has your clicker been clicking in, right? I need you to describe your performance like we just talked about, and then I need you to give yourself a grade. I need you to then say, I deserve an A. And you'll say, here's the evidence that I deserve an A. Here's the things that I've written and how well I've done. And if you're thinking to yourself, this is crazy, well, actually, this is how you will be graded for the rest of your life. Okay? For the rest of your life, in the normal world, no one gives you a 96%. It's just not how jobs work, right? You either perform and you get a raise or you get a bonus or you get to continue working at your job, or you don't, right? So you have to stand up for yourself and explain why you deserve that grade, that raise, whatever you want to call it, okay? And then here's what I'll give you. I'm going to review every packet. I know, it's crazy. We'll see. I'm going to try and do it very fast, but it's hard. So my weekend will be shitty. That's okay. It's just the Dodgers postseason, so I'm going to cry anyway. I'm going to look for full sentences. I want thoughtful explanations of your performance, okay? If I agree with you, your feedback will be brief. So this could be bad or good. You're like, hey, I think I'm getting a C in this, and I look at your work, and I'm like, yep, seems like C work. That's fine, right? Some people, it's a GE class. They don't give a shit. They're like, I'm almost out of here. I'm just listening because it's fun, and I'm ready to go. They're like, good. If I disagree with your grade, let's say I'm like, well, this is really actually B material, and I think you should give yourself more credit here, right? Then I'll ask you to improve your grade, right? Like, I think you deserve a B. You said C. The opposite's sometimes true. If I have everyone saying, oh, I deserve an A, I'll try and point out, well, maybe here sometimes you could be better, right? Because I have had folks come in and be like, oh, I'll take an A+. Like, we don't offer those. So, okay. I would give you a gold star, but that's just me. Is that fair? Everyone's still in agreement? No one's rioted. Census day passed, so you can't get out now. Right? Everyone knew that census day passed? Okay. Cool. So today we are really getting into the idea of, we talked about these planetary processes. What were the 4 planetary processes? And go ahead. One at a time. Tectonics, good. Volcanism, erosion. There you go. 4 planetary processes. Planetary surfaces can be changed by these 4 processes. Okay? In the homework, you'll be explaining which of them you can see. This will become a theme. Okay? You'll be open to interpretation. I want to hear your reason. Why do you think you see this process? Why do you think you see that process? So now we need to construct a model to understand why these different planets that we just saw on screen have the features that they do. Okay? So we started with Thanksgiving. We talked about this really helpful math that everyone loved and no one was confused by. So the basic point here is that the time for something to cool is proportional to how big it is. So if you take stuff out of the oven, a pea and a potato, you can eat the pea first because it cools down more, right? You have the potato, you have to open it, increase its surface area so that it cools down so you can eat it, right? Okay. Larger objects take longer to cool. So if we go back, we think about these objects here. Which of these cooled first? I see a point. Where? Series, very good. Which of these is still the warmest? Us, yeah. Right? Nice and wonderful to live here. Okay? That's the basic of it. Size plays an important role in the internal heat. Okay? So, oh God, already? All right. So let's ask this question. And we'll see whether or not folks were they went home, they really thought about it, they reflected, they did the reading. Okay. So this is the same question we had on Thursday. The lithosphere is the hard, cool outer layer of the planet. Remember that litho means rock. So this is the rocky exterior of the planet. Okay. Which planet should have the thickest lithosphere in terms of percentage of the planet's mantle / crust? Is it A, a large planet, B, a small planet, and then I messed this up and I forgot to change the standing. Okay, just imagine only C is there. C and D are the same answer, which is that the lithosphere should always be the same. Click in if you haven't. 50 answers so far. Okay, some folks did reflect on this. This is great. Anyone else want to buzz in? I'm going to close it in 3, 2, 1. Okay. So it's just between these two, large and small. So let's have a look. Come on now. All right. Lithosphere is the cool, rocky exterior. If there's a smaller planet which loses its heat more quickly, then that lithosphere grows into the planet and becomes thicker compared to the rest of it. If it's bigger, then the interior stays hot and melty and keeps the lithosphere a small fraction of the total. So here you can see the two large ones, a very small fraction of their lithosphere as the total planet. As opposed to Mars, which is smaller and cooled off earlier, has a very thick lithosphere compared to its total size. Right? Can't reach that, but that's like half. As opposed to this, which is like 10th in the stick diagram. Okay. Something weird is happening with Mercury. I'm not going to talk about Mercury. And the moon is basically all lithosphere until the core, all the way down, just cold as a rock. Okay. So smaller worlds cool off faster and their surfaces harden. Which of these objects is more likely to have volcanism? Oh, yes. I don't know why that happened. Yes, the ones with larger mantles and why? Yeah. The mantle has what comes out of volcanoes. This is really important, right? What comes out of volcanoes is magma that becomes lava. If you have a very thick lithosphere, it's like having a big lid that nothing can come through. But it's very thick, it's very difficult. Even if there was, and there probably is, some liquid mantle on Mars, there's no way it's making it through that lithosphere. Just so far to get through, right? Similarly with these two, but we won't talk about that. So if you have a very big planet, okay, like the Earth, and it has a small lithosphere, then the liquid that's in here can seep through the crust and come out in the form of lava, right? Volcans. Does that make sense? Anyone confused? Okay, so we're going to use this stuff. Okay, so we talk about these two on the end, Mercury and the moon, as being quote unquote geologically dead. They don't undergo any geologic resurfacing. They don't have tectonics. They don't have volcanism. Mars, kind of questionable as to whether or not there's tectonics, sea earthquakes, but what does that really mean? I'm not going to argue that here. Okay? So let's reduce everything we know about these planets to 3 fundamental qualities. Okay. One is the size. How big are you? The second is the distance from the sun. And the third is how quickly are you rotating? Can we do this one can we rank the planets in size? What's the biggest one of the terrestrial planets? Earth, good. Second, Venus. Mars. Mercury. Okay. Distance from the sun. That one's easier, right? Okay, what's the closest planet? Mercury. Then Venus. Earth. Mars. Good. Rotation rate. Should be good. All right, we'll see that in a few seconds.
Is that rotation rate around the sun or the day?
Yeah, this will be like the day. So what is its rotation rate? And we'll see this is really important when it comes to erosion. Because the rotation rate and weather go hand in hand. Weather is really important for erosion, obviously, because if you have something like wind and dunes that are created from wind, you need wind in the first place. Okay. Let's break these down. Because if I give you an object, and I will, you'll get a homework on this, or not hundreds. If I give you these 3 for a fictional planet, you should be able to tell me what you expect to find on its surface. That seem fair? Based on this model? Okay. How will distance from the sun matter? Well, of course, if you get closer, the surface gets hotter, right? If you get farther, it gets colder. Sun is just a giant campfire in a cosmic sense. Okay. Okay, and these affect all of the following. Okay. The size affects the gravity. If you're bigger, you have a stronger pull towards the center. And that also means that you'll have a higher internal temperature. The surface temperature is mostly dictated by how far away from that giant campfire you are. But it's a little bit moderated by whether or not you have an atmosphere. For example, Venus is not the closest planet, the sun, and yet its surface temperature is the highest. So you can only explain that with an atmosphere, right? And similarly, these 4 things affect those geologic processes that we just talked about. Okay. So let's really quickly talk about the processes that heat a planet. Okay. There's 3. One is stuff hitting it. That's called accretion. So basically, this process, we saw impact cratering, smash into the planet. Okay. There's obviously energy that's released when that happens, but also you've added material. So you've made the object bigger. Is that fair? Did you know that the Earth used to be smaller than it currently is? And we got a friend. And the friend took most of our crust and deposited a lot of stuff and decided it wanted to hang out forever until it drifts away. That's the moon. So the moon smashed into us, added material, made us larger. That process is called accretion, adding stuff to the object. Okay, then you have this one, differentiation. That is heavy go down, light go up. Very similar to hot go up, cold go down, right? But this is about the density. So if you have more dense material, it sinks. And the lighter stuff goes to the top. We talked about this in the context of separation in liquids. So if, for example, you have oil and water, and you put them in a cup for some reason, and you wait, they will separate. One will be on top, one will be on bottom. The denser one will be on bottom. In this case, the liquid is a combination of metal, silicates, some other stuff. The metal goes to the bottom. It makes the core. That's why it's this beautiful gray color. That's differentiation. Okay? The lightest stuff rises to the surface, and that forms the rocky crust that we stand on. Okay? Okay. Then you have radioactive decay. This is the fun one, right? Has anyone watched the HBO show Chernobyl? Pretty good, right? So that's happening in the interior of the planet. You have radioactive decay of uranium, and that creates heat. So it's very, very hot at the center of the planet, and it's continually staying hot. Okay, so accretion is no longer that big a deal. Otherwise, we'd be in a lot of trouble. We'd have to keep getting hit. But there's a source of heat in the interior, and that's radioactivity. Okay? You don't have to understand the details of radioactivity at all. But if you want to learn about it at the end of the semester, we can talk about it. These are the sources of heat. Is that fair? Okay. Which processes are significant today? Is it A, accretion, B, differentiation, C, radioactive decay, D, all of the above, or E, just differentiation and radioactive decay? Okay, interesting. There's like two camps. Can you click in if you haven't already? Okay, we're split between two answers essentially. So go ahead and ask your nearest neighbor if they chose D or E. Okay. And if they chose something different than you, try to convince them of your answer and vice versa. If they picked exactly what you picked, find someone else. Just turn another 45 degrees, right? Like, all right, if you successfully convinced your neighbor, click in, demonstrate that you're the best orator in the room. Oh, interesting. All right. Some people change their mind. Anyone want to defend their answer? Raise your hand. Let's hear from some new people today. Don't make me call you. Yeah. Okay. Why?
Because all of this, but accretion, that only really affects like the planet in its early stages, and we don't. It's just not a significant source. Not a lot.
Right. So accretion was like impact craters, right? Smashing into the surface, adding new material, adding heat, right? So if that was currently ongoing, we'd have trouble. When was the last major one? Dinosaurs. Yeah, it didn't work out well for them. About 66 million years ago, big accretion event, and like 90% of species died. So we're hoping that accretion is not a significant source of heat today. And radioactive decay and differentiation are. Okay? Differentiation, remember, is still hot goes up, cold goes down. Or dense stuff goes down, less dense stuff goes up. Right? So you have a balloon filled with helium, and you let go of it, it goes up. Make sense? Okay, and radioactive decay happens forever. That's Chernobyl, yeah.
Can you explain accretion a little bit more?
Yeah, accretion is just when you start with something and you start adding it. Adding, so you can look at the word accretion and think of the word adding. Like addition, but just change these with some special math to accretion.
What are some examples?
Impact crater. Yeah, just like this. So if you just if I hit anything into the planet, you would say that it accretes, it adds to it, and that increases the amount of heat.
That's where the dinosaur need, right? Okay.
We good?
How does it add to more of the size? You know, because you said it depends on the size, right? Say it's a smaller, maybe. I mean, its impact, how does it add to making it a bigger size?
Right. So we want to think about if you smash into something, right? Not only are you adding mass, but you're also adding how fast you're going. So if you make it 10 times larger, then you add 10 times the energy. But if you make it 10 times faster, you add 100 times the energy. So depending on what you smash into the earth, you can add different amounts of energy. Okay. So now let's talk about cooling really quick. Here's the 3 ways we cool the planet. Okay. So there's convection, conduction, and radiation. And I know this is going to get very confusing. I apologize for this in advance. Physicists not so good at naming things. Okay, and you're going to see why in a couple seconds. Convection is just like your oven. Okay, there's a convection setting. It makes air circulate to cook the turkey. I don't know why I'm only thinking about turkey today. Sorry. Okay, so this is the transport of energy as hot stuff rises and cool stuff falls. This process here takes heat from the interior and brings it out to the surface. Okay? It makes it to the edge, this rocky edge, and now the rocks don't want to move. They're rocks. So the only way that heat can get through them is through a process called conduction. And you have a very similar example if you're cooking. I don't know, all my analogies are food. I'm hungry. Okay, so you take a pan, and it's obviously not touching the fire itself, right? I mean, sometimes you cook directly on the fire, but in this case, you have a pan, you put, I don't know, an egg in there, and the egg cooks. That's because it's heated below, and the heat passes through the metal because all of the atoms in the metal are bumping into each other. So you move them, you make them bump more, and that makes the pan hot. That process is called conduction. Okay? So when things are physically touching, one thing's hot and one thing's cold, you pass heat from the hot thing to the cold thing. So you heat up the cool thing and you cool down the hot thing. Sorry if that's confusing. Yeah.
So like, to simplify it for me, the way I think of convection is like blowing on soup, and conduction is putting ice in a hot drink.
Correct. Yeah. So blowing would be using circulation, air, to draw energy from something. In this case, hot air is rising, right? So for example, if you just have your soup, you'll notice that the very top of it is the part where you see those, like if you're drinking miso soup, for example, you see these little cells. And there'll be places where cold soup is sinking and hot soup is rising. As opposed to when you're cooking, all of these, I don't know what to do. Just bear with me. In this case, if it's in contact, it's a lot worse, right? So for example, it hurts more to burn your hand on a hot stove than it does to put your hand in the oven for a few minutes, right? Don't do that, but you know what I mean. That makes sense? Okay. Last one's radiation, and this is the part that sucks because radiation we just used for that other process, that's radioactive decay. That's not what this is. It's the same words for different things. You can blame Marie Curie for these problems. Radiation is the transport of heat in the form of light. So currently you all see me, and I see all of you mostly, because light bounces off of you. But you are also emitting one. So if I were a snake, I could sense all of you because you're all warm. And therefore I could see that you're sitting there in front of something that is blocking the heat, right? For example, if I stand behind this, only the top part of me is emanating heat, and this is much cooler. So my skin, like 70, 80 degrees, and then this is hopefully not, right? So the process of transporting energy away as light is called radiation, when heat radiates, okay? This is the three processes by which we take energy from the interior of a planet and let it cool down. So in the interior, you have convection. Sometimes you have conduction as well in the metal core. Then it makes it to the surface. The surface is conductively cooled. And then once heat gets to the exterior, the only way for it to escape, since there's nothing in space to conduct away, space is the absence of stuff, the only thing it can do is radiate. And it radiates at a specific temperature. Yeah. Is this one weird? Okay. Let's ask a question. Let's see if we get this. Okay. Suppose a planet exactly like Mercury had formed, oops, that was running the whole time. All right. Suppose a planet exactly like Mercury had formed twice as far from the sun. How would its internal heat today compare to the real Mercury's internal heat today? Would A, fake Mercury have more internal heat? B, fake Mercury would have less internal heat? Or C, fake Mercury would have the same amount of internal heat? Okay. Is that everyone who wants to look in? All right, stop the count. Anyone want to defend their answer? What was that?
Is it C?
Is that your choice?
I'm not confident about it, but I'm betting.
You put B because it's further away from the sun. So B further away from the sun would change what part of the surface's heat? So let me say that differently. Okay. Hot campfire. I bring the thing closer. Does it change the interior or the exterior? Exterior. Okay. So the trick here is the word interior heat, internal heat. Do we still like B? Because a lot of you picked B.
Inside.
Almost all you picked B. Okay, so the word here is internal heat. External heat very much would be changed by moving away, right? So as I move away from the campfire, the external temperature goes down.
So do all planets have the same amount of heat? Or do-
Internally? Ah, very good question. Do all planets have the same internal heat? No, why not?
Like you were saying, it kind of depends on the processors and things, hit it using accretion, or it kind of depends on what's in the mantle, if there's more metals and not heating the core.
Okay.
I don't know if any other planets have radioactive stuff.
Yeah. So we haven't quite talked about what the planets are made of or how they formed or anything like that. But I did give you one rule about whether or not there's something internal heated. And it was the food analogy, one of many. Remember that one? What's that?
Sides.
Yeah, just behind you. The volcano tells you, the volcano tells you that there's internal magma, for sure. But what's the rule about size?
What if it is longer? Or the bigger something is longer?
The bigger something is, the longer it takes to cool, right? That's the internal temperature rule. So external temperature we get from distance from the sun. Internal temperature we get from size.
So that's why you specified a planet exactly like.
Exactly. Fake Mercury. And we'll have a lot of fake planets. And we'll move them and we'll make them bigger, we'll make them smaller, and we'll have you argue for why. On the homework, when you see this, because you inevitably will see this, I'm not trying to say that all of you need the same answer. In fact, I'll be shocked if you all have the same answer, but I want to see the reason, right? So if, for example, say on the homework that I've already put out there, there's an ambiguous question about volcanism, and you answer it, but you support your answer with reasoning, I will accept that. If you just say, here's my answer, and no explanation as to why you picked that, you will not do as well. Make sense? Okay. So size determines the internal heat. How much internal heat do you have? Okay. Distance tells you about the surface temperature. And then, of course, it's going to be different. We're going to talk about atmospheres. I really love atmospheres, so I'm hoping that that doesn't take like 15 weeks, but kind of do want it to take 15 weeks because they're the coolest. But we'll talk about how this is moderated by other processes. Okay. So let's do another thought example. What would the Earth be like if it was 10 times bigger, but rotated 100 times more slowly? Let's you think about that one. We're not going to answer it yet. We will be able to answer this soon. Similarly, what about 2 times smaller, but located 3 times closer to the sun? Okay. So let's tie these processes to the things we can see so that we can make predictions and we can use a model here. Okay. Most important one is planetary size. That influences basically all of the processes we've talked about. Here's Mercury, that's what it looks like. There's Venus, less impact cratering, for example. We need to explain why Earth has erosion and an atmosphere. We need to describe why the Earth's moon does not, even though they're at the same distance from the sun. We need to talk about what happened to Mars's like abundant liquid water. Where'd that go? Hint. And that's going to come down to these 3 different sizes here, or 3 different phenomena here. So first, let's talk about how planetary size affects volcanism and tectonics. Okay. So on the left, you have a small planet. On the right, you have a big planet. Small planet means that the internal heat gone, cooled off, right? And so there's nothing that's changing the surface from the interior. Remember that when we talked about tectonics, that is places where the interior is stretching the exterior. So this is our rigid crust at the exterior, and there's changes made because the interior is moving and it's trying to get heat out. Okay? So volcanism and tectonics requires a source of internal heat. Larger planets have more volcanism. Do we see that in the solar system? The 5 planets we just looked at? Which one has an active set of volcanoes that we know for sure? Us, right? Who's the biggest? Us, right? Okay, one data point. Venus looks really volcanic. We don't know for sure if there's active volcanism, but there's a lot of evidence that suggests that there's like plains, lava plains. Okay. Mars, did it have volcanoes at any time? Yeah, but it doesn't now. So at one point, the interior was probably liquid and it was able to have volcanism, but it stopped. Mercury and the moon, I guess that's a homework question. Okay, so big planets have more heat now, and they likely have more volcanism and tectonics. Now, we're not just talking about plate tectonics, we can also be talking about the fact that the surface is deforming. So you may see an object, right, that looks like it has concentric rings around something where the ground is being squished or maybe pulled, right? That's another form of tectonics. So this is the impact there. How does it impact erosion? Okay, so this is a long one. Let's see if we can get through this together. So small body likely doesn't produce a lot of volcanoes. Big body has a lot of volcanoes. These volcanoes produce gases, like we saw when we saw these Icelandic volcanoes that had these huge plumes. That's material from inside of the planet, gases coming out, contributing to the atmosphere. Okay? So that's a process called outgassing. Really great word name, right? Gas inside comes out, called outgassing. Okay. Now, can you have erosion? Well, that depends on whether or not you're too close or too far from the planet, from the sun. If you're too far, then it's too cold, and you could have erosion in the form of glaciers, but you really like liquid water. Liquid water is really good at eroding stuff, right? If you're super, super far away, the entire atmosphere will collapse and freeze out. If you're out like near Pluto, you have very strange atmospheres. Okay. And then I told you this, but I didn't give you any evidence for it. So you just have to believe me that rotation rate means more weather. So the faster that you rotate, the more violent your storms can be. Okay? So if you look at a planet like Venus, which has a very thick atmosphere, but only rotates once per year, then we should expect that the surface of Venus, there's almost no weather. And that's actually true. So we've landed on the surface, we have probes that go down there, little thing that spins and figures out how quickly the wind is going, and it's almost not moving at all. Whereas here, of course, you have hurricanes, right? Same size of the body, right? One's a little closer, okay? But something catastrophic happens. Okay? So these are the things that we care about erosion. Erosion requires a size which is large enough that volcanism existed, so that gas could come out, so that you could have an atmosphere. Then you need that atmosphere, ideally to have liquid water, but not a super big requirement. At some point, Mars had water. We'll talk about why that is when we talk about greenhouse effects. And then you need them to rotate. Okay. Okay, impact crater rate. The presence or absence of this has only to do with whether or not these other processes are present. So whether you're small or big, if you take an average size area, let's say you take, this big, you put this on the Earth, or you put this on the moon, and you count up how many impact craters hit both of those objects, it should be the same. There's no reason to suspect that the size of an object means that you would have more impact craters once you account for their size, right? They're not like pulling them in more. But if you are larger, you're more likely to have volcanism, tectonics, erosion, which will get rid of impact craters. So smaller bodies tend to appear to have more impacts. We probably have been hit as many times as the moon, but our surface is quite young. And so therefore, all of that information about how many times we've been hit in the past 4.5 billion years has been erased, right? Someone's constantly going over the whiteboard and removing all of the work that's been done. Does that make sense? Okay. This is probably what happened. We'll talk about the timeline of all of history if you want at the end of the semester. But the planets formed all at the same time. This is not quite right. We'll talk about why that is in a second. Okay, so let's assume the moon formed like right there. And then there was this weird period where a lot of stuff hit stuff. And we can tell that all these impacts basically happened at once by looking at the rate of impacts in certain regions. For example, we went to the moon, we picked up moon rocks, we find out how old they are. That allows us to compare different regions on the moon. Okay, younger regions have less impact craters than older regions. So that tells us about when these happened. So we get a little bit of cratering, a little bit of impacts throughout the course of the 4.5, but almost all of it's right here at the beginning. Okay. So if, for example, you had historic rates of impact cratering today, nothing, right? Just one little one in the Yucatan kills everything, right? Okay, now let me show you rotation. Better work. Yeah, let's go. Okay, that's the correct orientation and speed relative to one another. Do you want to see it again? Sorry. All right. Mercury, fast or slow? Slow, good. Venus, fast or slow? Very slow, right? Earth? Fast, pretty fast. Let's go again. Mars? Fast. Is that weird? Mars has almost the same length day. And it's almost tilted the same amount. Coincidence? Yes, yeah, it's coincidence. Yeah. Okay. Ceres, the one that I told you about earlier. Oh shit, it's not rotating. God damn it. I need to find the version that just goes on and on. Ceres, fast or slow? Faster, right? Okay, good. Jupiter? Rocket. It's doing it, right? Okay. Come on now. Saturn? Fast. Crazy fast, right? Uranus? Fine, yeah, it's still faster than us, for sure. What's it doing? It's straight up tilted like this. It's rotating on its side. Neptune? Kind of similar to us. That's pretty cool. You know? Think we should all be friends, right? What's Pluto doing? Pluto's in its own world, doing its own thing. Fast or slow? Pretty slow. Pretty slow. Venus, we really just passed over. Venus upside down. Venus rotates in the opposite direction to every other planet. But if you're Venusian, you think everyone's going the wrong direction, right? You live there in your little like Zeppelin or blimp, because you can't live at the surface, you're like, no, we're going the right way. You're all going the wrong way.
It's like the US.
Yeah, well, freedom units, yeah. Okay. All right. Well, I kind of got enough time for this. Okay. So we're gonna try to see if we understand what we just learned. Okay, we're gonna do another lecture tutorial. This one I made. So if you hate it, keep it yourself. Take two and pass them around, please. Do not do one alone, but don't do a group of like more than 4. Is that okay? More than 3. Don't do more than 3. You'll get there. One between 2 people. So 2 people work together. One between 2 people. One between 2 people. One between 2 people. 3 of them, then you pass it back. Or you can make a friend in it.
Yeah, you're right, because I know I saw it over there.
I do not have to go back up. I'll start.
That one, last one. So.
Yeah, there's no 4. 3 okay, 4 bad. That's okay. Are there extras?
Yeah. Yeah.
It's a secret. I didn't see one. Yeah.
So it's a.
Also, I think they know that.
Yes. Yeah.
Yeah. I don't think it was like they- yeah, the person gave up.
The bigger ones are smaller ones.
Yeah.
Yeah, no, I found yeah. Hopefully. So right now, one of those hanging around.
Because it takes longer.
Farther away.
That's hard to agree.
Oh, and then like I was like, what like shuffle twice, like I can get into it. I haven't, like, it's not-
Unless you want it.
I mean, I've just been looking for.
Oh, yeah, yeah. I just looked there. That was you handing it back to me. Yeah, yeah. Sorry.
I feel like more times like. Sure, that's.
What? I'll make it. Fine.
Oh.
Yeah, but that's I'm imagining like what is the service like if I. Yeah.
So that.
Okay, let's give it like 3 minutes. Are people mostly done? No? Halfway done? More than halfway done? Less than halfway done? Oh boy. All right. Sorry. All right. Well, let's give it 3 minutes anyway. You don't have to turn them in. You can turn them in on Thursday. your hand if you want to work on it for like 5 more minutes. Oh, okay. So. Sorry. Like the fact that we can't make it jump in.
Yeah, it's doing like. Just like.
Big look at the small. Bring up solve that more early on. Yeah. Thank you. That makes sense. Is a bigger. All right, 30 more seconds. All right, folks. Okay, folks. So, which of these objects have volcanic features that can be identified today? Is it Moon, Mercury, Mars, Venus, Earth? All of them? 4 of them, 3 of them, and so on and so forth. Okay, interesting. Okay. Let's talk about the geologic history of the moon just very quickly. We see that there are impacts there that have been recorded basically since the thing formed. We see volcanism because where there were massive impacts, the crust was weak and lava could seep through the thin lithosphere. That's a form of volcanism. That's not the type of volcanism that we traditionally think of, because I like to think of like big volcanoes, but that counts. If you have lava that seeps through the surface, that's lava going from the interior to the exterior. Definition of volcanism. Tectonics, this is when the crust itself compresses or extends, and that certainly happened. There are some wrinkles. There's not really erosion in a meaningful sense. There's definitely no wind. There's definitely no water. And moon is dead. Moon is dead, nothing changing. You step on the surface, it stays that way for millennia. Mercury, kind of similar. Okay. It was very it's very similar to the moon in size, but the interior is quite different, as we'll see. It's got a slightly younger surface. We can talk about why that is if you're really curious. There's this big feature that we talked about called the Calorus Basin, where you smack into one side and it forms some weird stuff on the back side. We definitely see actual volcanoes on Mercury. So we've seen volcanic vents and we've seen like the traditional form of a volcano there. We saw that there is lots of aligned ridges, like the whole planet itself shrunk. That's a form of tectonics. Anytime you see the crust deform, that's a form of tectonics. And maybe this is a questionable form of erosion. So there are places where there might have been icy material underneath the surface. And when it gets exposed to the sun, it melts away very quickly. And it creates these things called sink pits. Okay? Pretty much dead today as well. Venus, lots of craters. No, not very many craters at all. Less than 1,000. Mars has 600,000. The whole surface is quite young, about 600 to 700 million years old. Likely active today? Question. Okay. Tectonics, lots of it. Lots of places where the crust is deforming. No evidence of erosion. Why would that be?
It rotates itself.
Rotates very slow. There's no wind. There's definitely no water. And we'll see that when we talk about the atmosphere of Venus. It's about 700 degrees at the surface. Water doesn't like to be that hot. It's active. I'll call it active. There's Mars. Okay. This is the largest volcano in the solar system. That's Olympus Mons. That's the size of Arizona, if you recall. Impacts look like there was probably a lot of them. The northern hemisphere of Mars looks very different from the southern hemisphere of Mars. There's large volcanoes. Probably the largest canyon. Sorry, not the probably. The largest canyon in the solar system, Valles Marineris. I don't think we have time today, but you can like fly through it. Pretty cool. Like simulated, obviously. And then there is certainly erosional features, water erosion, etc. Okay. Thursday, homework. If you haven't turned in your homeworks, please do so here. Turn in lecture tutorials here and pick up your old homework so you can change them before you resubmit them next week. Yeah. If you finished it, if you didn't finish it, it's okay. You can turn it on Thursday.